good. Now let me share. Okay, so everybody can see the, sorry, this is not relevant. This is something else, but can you see the white board? You guys can see the whiteboard? Okay, good. So let's put it here and then carry on. Okay, so let's see, where are we? So we have done, we reached this point, we defined the null space of a, sorry, not, we defined the eigenspace of a matrix, eigenspace corresponding to an eigenvalue. We defined, we computed a couple of examples. So before going on, let's give a name. Let's see. So given, let's see, matrix, and an eigenvalue lambda. I don't know if I have already defined it. We call this space. So this is the null space of A minus lambda I is called the eigenspace. Okay, so this is called the eigenspace corresponding to lambda. So we have computed eigenvalues and eigenspace for several matrices. Just to make sure, we are now in, we are covering note 8, so which is eigen 1 according to the eCampus notes. And we covered up to, let's see, up to page 21. So we covered these examples where A was this matrix 1, 1, minus 1, 1, 1, 1, and 0, 0, 2. Okay, so let's carry on with the problems. Okay, so sometimes what would be given is some information about the matrix without exactly the matrix, something like this. So let A be 2 cross 2 matrix such that you are given that the determinant of A is 13 and the trace of A is 4. Okay, now find eigenvalues. So find the eigenvalues of A. So now when you see something like this, you know that you should always appeal to the equation, the polynomial. So how does the polynomial look like? So let's sometimes this is too fast for me. Okay, so how does the polynomial look like? So P lambda in this case, this is lambda square plus C1 lambda plus C2, right? So because A is a 2 cross 2 matrix. So we should have a polynomial of degree 2. Now, remember that C2 is the determinant of A, and C1 is given by the trace of A. Now, the roots of this equation, so the roots of P lambda gives the eigenvalues. Okay. And if you know a little bit about quadratic equation, you know that the sum of the roots is given by the trace of A, or let's say in this is given by C1, which is the trace, and the product is given by C2, which is the determinant. Right? Do you agree? So this is true. This part is true for any quadratic equation. So given a quadratic equation, the sum of the root is given by C1, and the product of the roots is given by C2. So the constant term and the coefficient for lambda. Okay, let's see. So once you have, so you have the sum of the roots, right? Now, if you want to solve this, if you want to get a system of equation, let's say, what you want is sort of the difference of the two, lambda 1 and lambda 2. So notice the following. So this is an identity. So if you take lambda 1 minus lambda 2, take the square. So this is lambda 1 plus lambda 2 square minus 4 times lambda 1 lambda 2, right? Any questions so far? So all of these are facts about quadratic equation or equations in general. So nothing extremely deep going on here. And now you can just plug in the values. So lambda 1 plus lambda 2 is what? Is the trace. So the trace is given to be 4. So this is 4 square minus, and the product, which is the determinant, is given by 13. So this is 16 minus 52, which is minus 36. So now you are in the territory of complex numbers. So you have lambda 1 minus lambda 2 square equals minus 36. So this means that lambda 1 minus lambda 2 has to be either 6 times I, where I is the complex number, so I square is minus 1, or minus 6 times I. Oh, this is too fancy. Okay. Then you can solve the equation. Okay, so then lambda 1 plus lambda 2 equals 4, and lambda 1 minus lambda 2. Now, the thing is that which equation you want to take. You can work with either 6i or minus 6i. Both will give you the same answers in an order. So if you take 6i and if you solve, so you can add the two equations. So you get 2 lambda 1 is 4 plus 6i. So then lambda 1 is 2 plus 3i. Hence, lambda 2 is 2 minus 3i. Okay. Now, if we work with lambda 1 minus lambda 2 equals minus 6i, then we get lambda 1 to be 2 minus 3i, and lambda 2 to be 2 plus 3i. So that's the only difference, nothing else. So you can work with either of the two solutions, let's say 6i or minus 6i. Okay, so that's that about the problem. The thing with this problem is that you have enough information to find the eigenvalues, but not enough information to find the eigen spaces or the eigenvectors, because you don't really know the matrix. What you know are these two informations. So there can be plenty of other matrices with these two informations, that they have the determinant 13 and trace 4. So in some sense, which we will see a little bit later when we do diagonalization, the eigenvalues and eigenvectors of a matrix together, they give you almost all the information about the matrix. So here, in a way, we have, let's say, half information. So we know the eigenvalues, but not the eigenvectors. Okay, so any questions about the solution? Maybe I pause for a couple of seconds for questions. If you are reading the notes, then you can, I mean, you already know what's going on. The point is, I am strictly following the notes because otherwise it will be a problem, because I'm not working on a blackboard anymore. Okay, so let's carry on. Oops. So if you look at the notes, the next problem is again pretty elementary in nature. So find eigenvalues and eigenvectors for this matrix. 2 minus 3, 1, then 1 minus 2, 1, and 1 minus 3, 2. Okay. So what I will do is to skip some details, because the details are already in the lecture notes, or maybe not. Sometimes I skip the details also on the lecture note. But the point is, P lambda is given by this determinant. Okay. And then if you work it out completely, so this equal to is a big one, so work this out. So this is lambda times or minus lambda times lambda minus 1 square. Okay. So then the eigenvalues, so the eigenvalues are given by the roots, of course. So lambda 1 equals 0 is one eigenvalue, is one eigenvalue. And lambda 2 equals lambda 3 equals 1. I'll write are the other eigenvalues. Okay, I mean, in the sense that 1 is an eigenvalue which appears twice. So this has, so maybe I'll make a remark. So 1 has what we call multiplicity 2, since it appears twice. Okay, so this has multiplicity 2 and 0 has multiplicity 1. So let's see, okay. So then the eigenspaces. So let's concentrate on the eigenspaces. So the first is related to 0. So E0, this is simply the null space of A. What is your A? So 2 minus 3, 1, then 1 minus 2, 1, 1 minus 3, 2. So this is the matrix A. And now, once again, you row reduce to get it down to the following matrix: 1, 0, minus 1, 0, 1, minus 1, and 0, 0, 0. Okay, I mean, I'm skipping, of course, this row reduction steps. So hence, so what do we have after row reduction? 1, 0, minus 1, 0, 1, minus 1, 0, 0, 0. Okay, so let's see, what does it give? It gives, from the first row, if you multiply, it gives x minus z equals 0, then y minus z equals 0, and that's it. So these are the two equations that we have, which means that x equals z and y equals z. Or in other words, x equals y equals z. Okay, so a general solution has this form. So all the components being same, so this is simply x times this specific vector, 1, 1, and 1. Okay, so what we get is that E of 0 is given simply by span of this particular vector. Okay, so this 1, 1, and 1, this vector is one particular eigenvector for this eigenvalue 0. But anything in the span of this vector is also an eigenvector. Okay, so any questions so far? I don't know why this gets blurred from time to time. So any questions about it? Especially for those of you who are not present. So we did problems exactly similar to the present problem in the last class. Okay, so then let's carry on. So similarly, E of 1. So this is null space. So this is null space of A minus I3. Now A minus I3, this is given by 1 minus 3, 1. That's pretty nice. So everything, so all the rows are same. So it's extremely easy to row reduce to just one row, one non-zero row, and the other two rows being 0. Okay. And we have only one equation. So we have only one equation, namely x minus 3y plus z equals 0. So from this, you should figure it out that span, so this E of, sorry, not 2, but 1. E of 1 is given by span of the following two vectors, 3, 1, 0, and minus 1, 0, 1. I mean, these are the two choices. You can have different choices, of course, but you should have these, I mean, two vectors which spans E of 1. And once again, you should check, so check that if you collect the three vectors which forms the different spanning sets, namely these three, forms the basis of R3. Okay, so that I leave it to you. So check that this forms a basis. So the easiest way would be to form, so this should be the columns of a particular matrix, and then find the determinant, and the determinant being non-zero will tell you that this set is linearly independent, and hence it's a basis. Okay, so any questions about this problem? It's clear. So you should open the lecture notes together with listening the lecture. Probably then you won't listen to the lecture because everything is done. Anyway, so the next example is for complex eigenvalues. So let's say you have A, which is this matrix. Oops. 1, 2, minus 2, and 1. So find eigenvalues and eigenvectors. I mean, in each and every problem, the beginning is the same. So in that sense, it's slightly boring. So A minus lambda I2. So this is what you want. And A minus lambda I2 is 1 minus lambda, 2, then minus 2, and 1 minus lambda. This is 0, means lambda minus 1 square plus 4 is 0. So now you can realize that you don't have any real roots of this equation, but you do have complex roots. So then lambda minus 1 square equals minus 4. So lambda minus 1 is given by either 2i or minus 2i, okay? As in the previous example that we solved. Oops. So hence the eigenvalues are lambda 1, 1 plus 2i, and lambda 2, 1 minus 2i. So if you notice, even in the first problem that we have done and here, the eigenvalues, if they are complex, they occur in complex conjugates, right? So 1 minus 2i is the complex conjugate of 1 plus 2i. So notice that lambda 2 is lambda 1 bar, okay? And it's not a I mean, it's not something very surprising if you know a fact about roots. The thing is that if lambda is a root of an equation, is a complex root of an equation, then the conjugate lambda bar is also a root. So let me state it here as a fact. So the above is not surprising, since if, let's say, p lambda equals lambda to the n plus c1 lambda to the n minus 1 plus cn is a polynomial such that, and this is important, such that c1, c2 up to cn are real numbers. Real numbers, and lambda is a complex root, then the conjugate is also a root of p lambda. Okay, you can try to show this. It's not very difficult. So the complex roots, they occur in pair. So if lambda is a root, lambda bar is a root. So hence, in this case, in this example, wow. So in this example, we have these two roots which are complex conjugate with each other. Okay, so let's find, so these are the two eigenvalues. So 1 plus 2i and 1 minus 2i. Now, what about the eigenvectors? So E of 1 plus 2i now. So this is complex eigenvalue. So this is null space of A minus 1 plus 2i, I2. So forget about complex numbers. The operations that you are doing should be exactly similar. So just remember that I square is 1, minus 1. So that's all it is. So you have A minus 1 plus 2i times I2. So this is given by, let's do this in detail, 1, 2, minus 2, 1, minus now 1 plus 2i, then 0, 0, and 1 plus 2i. So this is minus 2i, 2, minus 2, and minus 2i, which you can take the 2 out. So minus 2 times I minus 1, 1 and I. So everybody with me up to this point? So any questions about these operations here of E of 1 plus 2i? Okay, so then going forward, okay, so we need to, we need to row reduce this particular matrix here. Okay, so this is a matrix with complex entries. But then, once again, the only thing that you want to remember is that I square is minus 1. Okay, so using that, if you do the following operation, so R2 plus I times R1. So you're multiplying the first row by this complex number, I. So what is I times R1? So I square is minus 1. Sorry. So I square is minus 1. And minus 1 times I is minus I. So then if you add I times R1 to R2, what you get is the following. So the first row remains unchanged, but the second row gets completely vanished. So it's the 0 row. Okay, agree? So far, so good, I think. So then just plug in the variables. So we have I minus 1, 0, 0 times xy equals 0, 0. So this means I times x minus y equals 0. So that's the only equation that we have. Oops. Yeah, I have to practice controlling. That's the Okay, so then what it means is that y is equal to ix. So then a general solution is of this form. So xy equals x times ix. So this is x times 1I. So hence what we have is the following. So hence E of 1 plus 2I equals span of 1I. Okay. And similarly, if you work out the other eigenvalues, so similarly E of 1 minus 2I, so this would be span of 1 minus I. Okay. Now here also notice the following. The following thing, which is important. So notice that if you do the following, if you take the complex conjugate of 1 and I from the first eigenvector, so this is exactly 1 minus I. So this is the eigenvector for 1 minus 2I. Okay, so as if the eigenvectors, they also occur in complex conjugate, in the sense that you take the complex conjugate on each component. Okay, and this again is not by accident. So there is something going on. So which is the following. So let's, before going on, we leave an exercise. Find the complex eigenvalues and eigenspaces for this particular matrix, 1 minus 1, 1 and 1. Okay, so try this out. Okay, so this phenomenon that the eigenvectors that they occur in complex conjugate, or the eigenvalues occurs in complex conjugate, is not something by accident. Now we are moving to, where are we? So we have moved on to the second lecture, so eigen 2. So this is note 9. And now we will be in page 6 of note 9. Okay, so I might, maybe I'll give me a minute for you to open the lecture note. So note 9, page 6. So it starts with this fact. Okay, so this is the fact. So let A be an n cross n matrix, n cross n, sorry. Matrix such that all its entries are real. What does it mean? It means that A has this form Aij, and each entry is a real number. Okay. Then if lambda is an eigenvalue of A, with eigenvector, more space, with eigenvector x lambda, so that's the notation I used. So let's say this is x1 up to xn. If, okay, then as I mentioned before. So then lambda bar, or the complex conjugate of lambda, is also an eigenvalue. Eigenvalue of A with X. Now I use this sign. So I take the complex conjugate of each component, this as an eigenvector. Okay. First of all, is the statement clear? Otherwise, ask which part of, ask me questions about what is not clear. So A is a matrix which has real entries. Okay. So what this statement says is that if lambda is an eigenvalue, complex eigenvalue, let's say, maybe I should rewrite. So this is a complex eigenvalue with this particular eigenvector. So this entries x1 up to xn, they could be complex numbers. So what this statement says is that then the complex conjugate of lambda is also an eigenvalue with this particular vector, where you take the complex conjugate on each component, is also an eigenvector of A. Okay, so it's not really difficult to prove this. Once in a while, we should do a proof. So how does it work? So lambda is an eigenvalue, and this thing is an eigenvector. Means that the eigenvalue eigenvector equation is satisfied. So this is the equation. Okay, so that's the first observation. Now here is the point. Now, the thing is that we can take complex conjugate on both sides. Okay, so take complex conjugate, treat both of them as matrices and take complex conjugate. So which means that A x lambda bar, so this is the complex conjugate, is lambda x lambda bar. Okay, and using the property that Z1 Z2 conjugate is Z1 conjugate times Z2 conjugate, we get that this is A conjugate times X lambda conjugate, in that sense, equals lambda conjugate times X lambda conjugate. Okay, now here is the fact. Here is where A being a real matrix is used. So all the entries of A are real. Okay, so then A conjugate, which is Aij conjugate. So this is the same as A. Okay, because each entry is real, so this is exactly A. Hence, we are almost there. So what do we have? We have, so we get A times this particular vector, which is obtained by taking the complex conjugate. This equals lambda bar times the same vector. Okay, so we have another eigenvalue eigenvector equation for A. Right now, this is the eigenvector for lambda bar. So that basically proves the fact. So that lambda bar is also an eigenvalue with this particular eigenvector. Okay, so whenever you are working with complex matrices, or rather you are working with complex eigenvalues, you can right away say that the conjugate is also an eigenvalue. And if you find an eigenvector for a particular complex eigenvalue, at once you can know that if you take the complex conjugate of that eigenvector, it will be an eigenvector for the complex conjugate of the eigenvalue. So there is this nice parity. So a good way to remember maybe is the following notation. So you have lambda x lambda, then lambda bar x lambda bar. So both are eigenvalue, eigenvector pair for A. Okay. Once again, any questions up to this point? Okay, seems like you guys were ready for the lecture today. Let's see. So this is where we did the proof. Okay, now we switch on to something we started off with. So remember, at the very beginning, I think Bob talked about this, that eigenvalues and eigenvectors, they occur in differential equations. I mean, in a way that differential equations occur in nature. I mean, many practical problems can be formalized through differential equations. And eigenvalues and eigenvectors are used to solve differential equations, or at least first order differential equations. So that's where we are going right now. We saw one concrete example. So given a differential equation, we used eigenvalue and eigenvectors to solve it. So now let's generalize that particular idea. So system of differential equations and eigenvalue, eigenvectors. So what do we have? We have, so instead of an n cross n system of linear equations, we now have an n cross n system of first order differential equations. So let us be given n cross n system of, differential first order Okay, so how do they look like? So u1 prime equals, so I'm following exactly the lecture note. So this is our system. Remember that ui prime is simply dui dt. So the t is the parameter and ui depends on t. So ui is a really ui as a function of t. Okay, so this is a first order linear differential system of differential equations. So almost like a linear system of equations, just that you have differential equations. Questions? Okay, so let's continue. Okay. So what we do is something exactly similar to system of equations. We arrange it in terms of coefficient matrix, then a vector, now vector of functions. And on the right hand side, we have the vector of differential equations. So something like this. So A11, A1n, okay, so and the multiplication is matrix multiplication, although these are functions. So this is, I mean, the left hand side should be read as A11 U1 plus A12 U2 up to A1 and UN, and for each row. So the last equation, or the last, last equation is an1 times u1 up to ann times un, and equate with the right hand side. Okay, so let's call this matrix A. So this is once again called the coefficient. This is called the coefficient matrix of the system. Okay. So then let's give some names. So A is the coefficient matrix. Let's call U to be this vector of functions, and U prime simply the derivatives. Okay, so you have AU equals U prime. Now, if you remember how we solved the first problem of differential equations, so something exactly similar is going to happen. So what we want is to choose a certain type of functions for our U1 up to UN, and then try to figure out for what conditions those functions would be a solution. Okay, so we choose U1 equals, let's say, alpha 1 e to the lambda t, U2 alpha 2 e to the lambda t, UN equals alpha n e to the lambda t as a set of n functions. So let U be this vector of functions. So e to the lambda t up to alpha n e to the lambda t. Okay, so we want U to be a solution. Okay, so we want this. So hence we want to find conditions on lambda and this alpha 1 up to alpha n. Okay, exactly as in the problem, in the first problem that we did, or that Bob did, to be more precise. Once again, let's call alpha bar this vector alpha 1 up to alpha n. Then U can be written as alpha bar e to the lambda t. Okay. Now, if this, so if U is a solution, then it satisfies AU equals U prime, right? Now, U prime is obtained by taking the derivatives on each component. So U prime is given by lambda alpha 1 So lambda alpha 1, alpha 2 up to alpha n times e to the lambda t. I mean, you just take the derivative on each component. So each component, the derivative is given by lambda alpha I e to the lambda t, and hence you can take out alpha lambda. This remains same, the vector alpha 1 up to alpha n, and then e to the lambda t. Okay. And if you plug in, so you have a, so u was, what was u? Let's see, alpha bar e to the lambda t equals, now lambda, this is alpha under bar e to the lambda t. Okay. Now, once again, e to the lambda t is not 0, right? So it's a real number which is never 0. So we can cancel this out. And we are left with exactly an eigenvalue, eigenvector equation. Right? So what it means is that alpha has to be an eigenvalue, rather not alpha, but lambda. So lambda has to be an eigenvalue, and this has to be an eigenvector. Okay, so if we want to solve a differential equation using this sort of functions, which is in a sense the standard functions that one uses, then these are the restrictions. So I mean, lambda has to be an eigenvalue, and the corresponding alpha under bar, that has to be an eigenvector. So in this way, the example that we did at the very beginning of this chapter, let's say, is generalized here. If you realize, I mean, what we did for that example is exactly similar to what we did here, but in that example, that's it. Okay, so then we have figured out when we have a solution. So now, if you have two such solutions, let U1 and U2, which is, let's say, alpha 2 under bar e to the lambda 2t, be two solutions. Then if you take a linear combination, so S times U1 plus T times U2, then you can check that this U is also a solution. So if, let's say, lambda 1, lambda 2 up to lambda n are the eigenvalues, of the coefficient matrix and let's say alpha 1 under bar, alpha 2 under bar, alpha n under bar, the corresponding eigenvectors. Then a general solution, so this is called a general solution of the system is given by this new function. So u, what you can take is s1 times alpha 1 underbar e to the lambda 1 t plus s2 alpha 2 bar e to the lambda 2 t Sn alpha n underbar e to the lambda n t for different choices of this scalars S1 up to Sn. So different choices of S1 up to Sn, what is the S? Oh, here, okay, so S and T are scalars. So you take a linear combination of the two solutions, you get another solution. So that is the philosophy. So at the end, let's say if lambda 1 up to lambda n are n eigenvalues with corresponding eigenvectors, you take a linear combination of those of those functions. So alpha 1 under, sorry, alpha 1 underbar e to the lambda 1 t, alpha 2 underbar e to the lambda 2 t, etc. That will be a general solution. Okay. So is it clear what is S? S is a real number. I mean, real or complex number. Okay, now this is somewhat somewhat a deep question is the following, that okay, so you have this solution, general solution, but can you guarantee that this is the only possible solution? So any solution of this system of the system of differential equation has this form, this u. So S1 alpha 1 underbar e to the lambda 1 t, etc. So this is a rather deep question. So let's just state it as a fact. Okay. Well, let's leave it for the later, because there is something else that we will do, and this fact could be stated more efficiently at that point. So we will see that under certain circumstances, these are the only solutions of a given differential equation. Anyway, so this is a general solution. So what is an initial value problem? So we will end by defining this initial value problem. A system of differential equations. So AU equals U prime is called an initial value problem when particular value is given at a certain time. So usually at t equals 0. So for example, you have u1. So these are the n functions, right? U and t. So initial value means the following, that you are given u1 0 equals say c1, u2 0, c2 up to un 0 is cn. So you're given particular choices for a certain time t. So with that constraint, you can solve this. The first thing is solving this system of equations. And once you do that, you plug in this value, t equals 0. So you have c1 up to cn. What you get is a system of equations, linear system of equations. So in the following sense. So you have this solution, let's say u1 up to un. So this is given by s1 alpha 1 bar e to the lambda t plus s2 alpha 2 bar e to the lambda 2t plus sn alpha n bar e to the lambda nt. Okay. Now at t equals 0, what happens? On the right hand side, e to the lambda I 0. So e to the 0 is 1. Okay. So what you have is this following system. So u1 0, un 0 is given by s1 alpha 1 under bar plus s2 alpha 2 under bar. Okay. And if you recognize, this is nothing but a linear system of equations. So given an initial value, you have this linear system of equations and you can solve it. So you solve it for S1 and Sn, S1, S2 up to Sn. So then you get a particular solution. So solving for S1 up to Sn gives a particular solution. Okay, so that's about it for the class. So what we do, probably next Thursday, because Tuesday is our exam. So what we do is we solve a couple of problems about this differential equation, and then we move on to diagonalization. Okay, so any questions from your part? Otherwise, I will end the session now. When will the exam be posted? So it will be posted on Tuesday, March 31st, around 2:30. So class time. Maybe I'll write it. Is this lecture? No. I will just ask, well, this is, I mean, I'll just ask simple problems on eigenvalues and eigenvectors. So, for example, nothing related to differential equations. Well, we did problems on eigenvalues and eigenvectors today. So you can consider those problems. For example, what we did at the beginning of the class, let's say. So problems on eigenvalues and eigenvectors. So those sort of problems will be there. Okay, this is March 31st around 2:30. Yeah, so this is a good question. So it's a take-home exam. So I leave it up to you. Well, everything is, so the information about exam has been posted already. So you have a couple of days. So April 2nd, till April 2nd to complete it. When will the lecture be posted online? Sometime today at night. Yeah, but this is something we should discuss. Will we learn new material on the day of the exam? So what do you want? I mean, I can do a very short class, like half an hour, to do some new materials, because I mean, we already lost a week and the exam is take home. So you can basically do it after class or sometime later. So let me know what you want to do. I mean, discuss among yourself. I can teach for half an hour and then end the class. So it will be a very short lecture. Or I can just post the exam and that's it. I'll be online maybe for some time so that you can ask something about the exam if there are questions which are not clear in the exam, and that's it. I won't teach anything new. So, I mean, that's up to you. Anything else for the moment? So I'll come back at 4 for the second class. Okay, if not, okay, so yeah, so I still have another lecture to go. So let's meet on Tuesday and have a great weekend. Stay safe, have fun at your home, I guess, and bye.